of your homework tonight show that the set of decidable languages is closed under union. Let's prove that. Uh, let's say definitions. A decidable language is a language that can be recognized by a fixed Turing machine. The union of two languages, A and B, we have A and B, contains all strings that are in either A or B. Crime will prove that if languages A and B are decidable, if these are decidable, then their union A union B is also decidable. So uh, A, B, and B are decidable. Then A union, let's compact A union B is also decidable. Uh, Now we will prove that. Okay. Proof strategy. Assume we have decision Turing machines for languages A and B. For A and B, we have uh, Turing machines, and construction of the decision Turing machine lets MA and MB be the decision Turing machines for A and B, respectively. A decision procedure for A union B, let's give an example here, would work as follows. For example, we have decision procedure, let's say we, and uh, we have run the decision machine for A on input we. Second one, if mi accepts we accept, and third one is run, sorry, third one third one is run the decision uh, machine for B on input B, sorry, V. Uh, Fourth one, if and B uh, accepts W accepts, and lastly, otherwise reject. This is an example for a union B. Uh, Now, correctness argument, let's say correctness argument. If W element of A, the first step will cause acceptance. If with element of B, uh, the second step will cause acceptance. If W not element of A and not element of B, the procedure will reject. If we element of A and element of B, first step and second step will cause acceptance, but if uh, W not element of A and not element of B, the procedure will reject. This ensures that the machine correctly correctly decides the language A union B. Okay, the set of decidable languages is closed under. For this example, the proof demonstrates that when we have decision procedures for two languages, we can construct a decision procedure for their union by simply trying both procedures sequentially. This is proof of the question. The second question. Show that the set of decidable languages close under complementation. Before the proof, let's we have A. We know that this is uh, let's be decidable, and for this question, A complements also decidable. How? Uh, let's prove. Okay. This is the actual claim. A decidable, A complement is also decidable. In this question, our goal is prove that if A is decidable language, then its complement A complement is also decidable. Construction. Let's give a decision Turing machine M for languages A. Turing machines for language A. Then create a new machine. Create a new machine M complement that uh, runs M on inputs on the inputs. Okay, and accepts if M rejects and rejects if M accepts. Let's say correctness. Let's write if we element of A M accepts M complement rejects. If not element of A and M rejects M complement accepts. This is the correctness. Okay. Ensures A is corrected decidable. After this, we can decide uh, A complement is correctly decidable. Okay. Same computational complexity as original machine. Termination and decidability preserved. Decidable languages are closed under complementation. We proved that. Okay, so A decidable and A complement decidable. We showed here. The third question show that the set of recognizable languages is closed under union. In this question, our goal is prove that if A and B are recognizable, that's right, A and B are recognizable, and then A union union B is also recognizable. We prove that uh, now. Create a Turing machine and let's uh, create a Turing machine, and that runs recognizers for A and B in parallel. A and B, let's type B in parallel, except if either recognizer accepts continues running if no exceptions occurs. Now let's like the one and second questions. In here we are again right correctness. That's right. If we element of A, element symbols, element of A, uh, and A accepts if uh, the element of uh, B and B also accepts, and if the not element of not element of A and will not element of B may run uh, ident- identically. Uh, in this question, we can say parallel simulation of both language recognizers, non-termination allowed for strings outside the union, and preserves recognizability properties. Uh, and so, recognizable languages are closed under union. The proof shows how recognizable languages can be combined while maintaining their fundamental uh, computational characteristics. That is the answer of the third question. Okay, fourth question. Determine whether the language of all Turing machines that accept nothing is recursively enumerable or not. Now, here's the language of all Turing machines that accept nothing is not recursively enumerable. How? What is the reason? Determining if a Turing machines accepts no strings is equivalent to solving the halting problem. The halting problem is undecidable. Therefore, we cannot enumerate such Turing machines. If it were recursively, we could solve the halting problem, which is impossible. Proof technique, how we uh, can prove that contradiction, assuming it is recursively enumerable, would mean solving a halting problem. Solving the halting problem is an important point. This contradicts the known undecidability of the halting problem. Uh, so this is not recursively enumerable. So the "k" inside is the direct connection to the undecidability of the halting problem, which prevents any algorithm and enumeration of this Turing machine. Okay, this answer of question is not recursively enumerable. This is the answer, not. Yeah. The last question: determine whether the complement of the language of all Turing machines that accept nothing is recursively enumerable or not. Let's start the answer. Uh, Complement language. By the way, what is the complement? For example, we have A. Uh, what is the complement of A? We can write like this. Uh, all Turing machines that accept at least one string, uh, that accept Turing machines at one string, at least one string. Let's make analysis. We can generate a list of such Turing machines. What's the method? Systematically enumerate inputs for each Turing machine. If a Turing machine accepts any input, we include it. Let's prove this question. What is the proof strategy? Creates an algorithm that generates Turing machines systematically. Tests. uh, First, we will generate Turing machines systematically, and the other one is we will make a test inputs for each Turing machine. And last one, the last strategy of proof, lists those with at least one accepted string. Uh, the complement language recursively enumerable. Unlike the original language, this one can be algorithmically listed. Okay, this is the answer. This question, complementing the empty language Turing machines produces a listable set.